This video introduces our CVPR 2025 paper, Toward Real-World BEV Perception, Depth Uncertainty Estimation via Gaussian Splatting. In this work, we study bird's-eye view perception, a core task in autonomous driving that provides a unified and interpretable top-down view of the environment. Recent state-of-the-art BEV perception models rely on projection-based query learning, which bypasses explicit depth estimation and has shown strong performance in benchmarks. However, these methods still fall short in real-world deployment. They lack uncertainty modeling, making them less robust in ambiguous scenes, and often require significant computational resources. In this work, we present an uncertainty-aware BEV perception framework that revisits the unprojection-based lift-splat-shoot paradigm. Our method enhances this classical approach by explicitly modeling depth uncertainty, allowing the network to reason about spatial ambiguity and object extents more effectively. We compare the lifting mechanisms of lift-splat-shoot and our proposed method. Lift-splat-shoot uses discrete depth probabilities to compute soft weights along predefined depth bins. While effective, this approach suffers from depth ambiguity, as depth estimation is inherently ill-posed. Moreover, the softmax-based depth distribution can produce unstable probabilities, where nearby depth bins receive inconsistent weights, leading to discontinuous and sparse BEV projections. To address these issues, we introduce an uncertainty-aware approach. Instead of relying on discrete softmax weights, we compute the mean and variance of the predicted depth distribution, and model it as a continuous Gaussian. This enables us to project features within an adaptive range, where we introduce an error tolerance coefficient k that controls the spatial spread. In this step, we transform the predicted depth distribution into a 3D uncertainty-aware representation. First, we unproject each depth bin into 3D coordinates using the camera's intrinsic and extrinsic parameters. This maps each pixel into a set of candidate 3D points. We then compute the 3D mean position and the covariance matrix, based on the predicted depth probabilities. This allows us to represent each pixel as a 3D Gaussian, where the mean captures the expected location in space, and the covariance encodes its spatial uncertainty. Visually, this uncertainty is modeled as a 3D ellipsoid centered at μ3D, providing a compact and informative way to express confidence in the estimated 3D structure. After transforming the depth distribution into a 3D Gaussian, we proceed to render features onto the BEV plane using Gaussian splatting. For each pixel, we first extract its multiview feature vector f and the predicted opacity alpha. These are then combined with the previously computed 3D Gaussian parameters, the mean μ3D and covariance sigma, to form a set of spatially aware feature Gaussians. We then apply Gaussian splatting with alpha blending, a differentiable rendering technique that smoothly distributes features onto the BEV plane. Unlike traditional splatting that blends RGB values, we replace color with feature vectors, allowing us to construct a dense and uncertainty-aware BEV representation directly from 3D Gaussians. We begin by processing multi-view images with a shared backbone network to extract visual features. These features are then passed through a lightweight CNN to produce three key outputs for each pixel: the splat feature Fi, the opacity alpha I, and the depth distribution Pi. The predicted depth distribution is transformed into a 3D uncertainty representation, denoted as Xi, which includes the 3D mean and covariance. Next, we perform Gaussian splatting, aggregating features across multiple views onto the BEV plane, while preserving spatial uncertainty. The resulting BEV feature map, FBEV, encodes both appearance and geometric uncertainty, and is fed into a task-specific head for downstream predictions. This table shows the BEV segmentation IOU for the vehicle class on the new scenes dataset. We compare our method against both projection-based and unprojection-based baselines under 4 different evaluation settings, incorporating visibility filtering in 2 resolution levels, following the protocol from Point BEV. The upper rows list projection-based methods, while the lower rows show unprojection-based approaches. Across all settings, our method consistently outperforms other unprojection-based methods, establishing state-of-the-art performance in this category. We further evaluate our method on pedestrian segmentation. At 224 by 480 resolution with visibility filtering, it outperforms all unprojection-based baselines and is only 0.5% behind the best projection-based method, showing strong performance on small object categories. To assess generalization, we also apply it to map segmentation and 3D object detection. As shown in Table 3, our method achieves competitive results on map segmentation. For 3D detection, we integrate a detection head into our BEV features, following BEV former. As shown in Table 4, our method performs well in both MAP and NDS, highlighting its effectiveness beyond segmentation. Last, we compare our method on inference speed, memory usage, and vehicle segmentation IOU across different baselines. Our method achieves comparable IOU to point BEV, with only a 0.4% difference, while offering over 2.5 times faster inference and using just 1/3 of the memory. We provide a strong trade-off between accuracy, efficiency, and deployability, making it well-suited for real-time autonomous driving applications. In summary, we introduce a novel BEV segmentation framework that explicitly models depth uncertainty by transforming soft depth distributions into 3D Gaussians. We leverage Gaussian splatting to render features onto the BEV plane in a way that preserves spatial uncertainty, enabling smoother and more reliable representations. Our method achieves state-of-the-art performance among unprojection-based baselines, while offering significantly better inference speed and memory efficiency. These results suggest that our method is both accurate and practical, making it a promising direction for real-time autonomous driving systems.